All right, hey AP Chemistry. Here's another video on how I would do what's known as buffer calculations. I'm going to try and show you the longer way using an ice table if you don't know how to use a certain other equation. And then I'm going to show you the simplified way of using a very fancy equation to do all this math quickly. So let's say I have HCN, which has a Ka of 4.9 times 10 to the minus 10th, and I mix 0.1 molar of HCN with 0.2 molar of NaCN into a constant volume, and I'm asking, what is the pH of this solution? Now, a couple of things. When I'm asking for what's the pH, I cannot automatically use the concentration of the acid. Why? Well, in a previous video, I mentioned that this is a weak acid, so the concentration of this acid is not equal to the concentration of the H plus that forms. I need to figure out how much H plus, and then I put its conjugate base Cn kind of secretly hidden in there. Don't forget about our ions business here. I have Na plus and Cn minus here. So if I throw that in here, Cn minus is very important for HCN. So if I have a question like this, it doesn't matter how you write this. You could do the acid association or the base association. Let me just do the simple acid association. I'll do aqueous plus H2O, liquid, in equilibrium with H3O plus, aqueous, plus Cn minus, aqueous. Okay? Now, if I have a mixture of an acid and its conjugate base, and how do I know what's its conjugate base? Well, this isn't HCN, this is NaCN. That NaCN came from Na plus and Cn minus, and this Cn minus is the only common ion with HCN, so that must mean that it's its conjugate base. If I mix an acid and its conjugate base, I make what's known as a buffer. Okay, so let's try and do some calculations here using an ice table. And we've done a calculation like this before. If I give you two initial concentrations, what are my final concentrations? Well, it depends on how you know how to read and interpret an ice table. So if I'm doing an ice table, what do I have initially? Well, I have initially 0.1 molar of the HCN. Water gets ignored. It has a concentration of 55.55 molar, and that's constant. That's just a fun fact there. I don't know my H3O plus yet. I'm going to say that that's 0 in the beginning. All right, no, not a question mark. It is. It's 0 in the beginning. However, can I say that I have 0 Cn minus initially? No, because I give you 0.2 molar of NaCN. And so if I have 0.2 molar NaCN, 0.2 molar of NaCN, the ions are in a 1-to-1 ratio. That means I'll have 0.2 molar Na, and I'll get 0.2 molar Cn minus. So initially, I'll have a concentration of 0.2 molar Cn minus. And so now what do I do if I want to carry out the calculations? I have to be careful because I have two initial concentrations. That's really the only difference in a buffer calculation. We've done calculations like this in chapter 15 where I give you two initials and then I have to follow through with the ice table. So now in my change, my reactants get used up. So minus X plus X, I'll get more H2O plus X, I may get more Cn minus. At equilibrium, I should get 0.100 molar minus X, 0.200 molar plus X. And now I'm going to write my Ka expression. In my previous video, I really showed you step by step how to write the Ka. I'm going to simplify it now. So I should do my products over my reactants. I should have X over 0.200 plus X all over 0.100 minus X. And I'm just going to ignore the M for now because I just want to do the math. Right? So I put my products, the products of my products over on the top, my reactants on the bottom. And I exclude water because liquids and solids are not included in the equilibrium expression. So now this is equal to 4.9 times 10 to the minus 10th. That is a very small Ka, huh? So what can I do? Well, I know that this x can be assumed to be small, that it's negligible. So now I'm going to go down and say Ka is equal to x 0.200 plus x over 0.1. But I have another x all over here. If minus x is negligible, then plus x can also be negligible. If I'm adding or subtracting a very small number, I'm probably going to get the original number back, which means my equilibrium concentrations are going to be pretty close to 0.2 and 0.1. So now I could actually simplify this equation even more and say that my Ka is equal to x times 0.200 over 0.100, which is equal to 4.9 times 10 to the minus 10th. And I could actually, or I don't have to do any quadratics now. This has gotten so much simpler. I could try and simplify this expression because 0.2 over 0.1, that's just equal to 2. 0.2 over 0.1 is equal to 2. So now I'll get 2x, because 2 times x is 2x. 2x is equal to 4.9 times 10 to the minus 10th. If I want to solve for x, divide both sides by 2. 4.9 times 10 raised to the minus 10th divided by 2. I get x is equal to 2.45 times 10 to the minus 10th. Okay, so now I know that my value of x is here. That's going to be my acid, my H3O plus concentration. Right, so I didn't have to do quadratic. I cancel out the x in the top and the bottom. This has become a simpler calculation. So if my x is equal to 2.45 times 10 to the minus 10th, that means, according to my equilibrium from the ice table, my x is equal to my concentration of H3O plus, which is equal to 2.45 times 10 to the minus 10th. If I want to figure out the pH, pH is equal to the negative log of the concentration of H3O plus, which is equal to the negative log of 2.45 times 10 to the minus 10th. All right, so I know I'm squishing it in here and I'm sorry. Negative log of 2.45 times 10 raised to the minus 10th, and I get 9.61. Okay, so that's my pH for this mixture. That's quite high. It's basic. And maybe that makes sense because I have more base added in here than acid. Now I'm going to show you the easiest way to do this. All right. So there's this beautiful equation that's the Henderson Hasselbach equation that says pH is equal to the pKa plus the log of the concentration of base over the concentration of acid. Okay. Now I know that my Ka is equal to 4.9 times 10 to the minus 10th. The pKa, the negative log of Ka, I don't know if you've guessed this, the negative log of Ka is equal to the pKa. And we use pKa as a simplified way of figuring out of using like whether an acid is stronger or weaker, because it's a mouthful to keep on saying 4.9 times 10 to the minus 10th, but it's easier to just say pKa. So negative log of 4.9 times 10 raised to the minus 10 is equal to 9.3098. I'm going to just keep all those sig figs in there. So the negative log of the 4.9 times 10 to the minus 10th is 9.3098. I'm going to plug that into this equation here. If I want to figure out the pH, I'm going to use pKa plus the log of my concentration of base over acid. Guess what? I gave you that in this problem. I said concentration of base was 0.2 molar and my concentration of acid was 0.1 molar. So it becomes the log of 0.200 over 0.100. So now I'm just going to do 9.3098 plus the log of 2, right? 0.2 over 0.1 is the log of 2. The log of 2 is 0.3010. Okay? And so if I'm doing this math here, and if I'm trying to do it correctly, I'll get pH is equal to 9.6. I'm just adding this together. So 9.3098 plus 0.3010. I'll get 9.61, which is still basic. Now it's different than our answer. Slightly different. Actually, no, it's the exact same. Oh, my bad. It's the exact same. Never mind. I thought it was 9.31. I was kind of doing it slow because I thought it messed up. But no. Oh my goodness. Look at this. Our pH is the same if I use the ice table or if I use this fancy equation. So if you're ever given an acid and its conjugate base, do you have to use an ice table? No, you could use this lovely equation known as the Henderson Hasselbach equation. And it's an equation that it's given to you on the AP Chem exam. It's on the reference sheet. And if you know how to use it, it's very simple. You use this equation for an acid and conjugate base combination. And you get the same answer. My pH is 9.61. Using all of this work, I still get my pH is 9.61. So that's the amazing thing here. So that is how you do a buffer calculation. A buffer calculation is kind of like if I had an equilibrium calculation with two initial concentrations or two initial amounts. Don't forget to convert everything to concentrations here. If I mixed volumes, then you have to add those new volumes together. So if I had like 100 milliliters of this and 100 milliliters of that, you'd have to be careful because the new volume would be 200 and I'd have new concentrations. And that would be a more tougher, challenging problem to consider, but that has to do with dilutions. So combine dilutions with a question that was like that. I assumed constant volume, so I tried to make this calculation straightforward. So in general, if you don't remember the Henderson-Hasselbach equation, you could use an ice table, but you end up getting the same freaking answer if you use the Henderson-Hasselbach equation. All right, so I'm hoping this video was helpful. Comment or comment on the video or message me in the remind if you still have any questions or concerns on how to do buffer calculations or what a buffer is.